Okay, hi, Math 2504. Good afternoon, good midday if anybody is in China. I don't think we have students elsewhere. Welcome to week 7. Nice of you to continue to come both to Zoom and to the class. I must say I'm excited teaching in person. It's not something I've done for a while. I might not do it for a while also. So nice to have you here. Okay, so just a roadmap of where we are. So today, basically, with me, Yoni, for about just under 2 hours, we're going to finish our Julia crash course, really. So Unit 4, a whole bunch of code, a whole bunch of features, not a whole bunch of graphics, like zero graphics, right? You had all the interesting stuff with Paul Bellet. You saw exciting things, etc. Mathematics. With me, you're now going to fill in some gaps in the language. The most important thing in terms of gaps is learning the type system, okay? And then we'll pretty much part ways, you and me, in terms of lecturing. And tomorrow, Paul Verbeek will start with symbolic computation and give you an overview of that. And that's, of course, related to your project. So as you have seen, you've got here project 1, and it's here. And that's due in just under 3 weeks. Now, the key to this project is going to this existing project. We already did it for you. So all you need is you just need to resubmit a repo. And well, okay, that'll give you maybe 20 or 30% of the grade. But then you do a few modifications to this project. So you already have quite a lot of code here. And over the coming days, what I suggest is to start digging into these code and asking in Piazza, hey, what's this and what's that and what's this and what's that? So understanding the thing that exists here already, we'll modify it still a bit because we're all last minute people. So there still needs to be a bit more for the factorization. But pretty much this code base exists and you'll be modifying this in the project. It shouldn't be so difficult, especially given the steep learning curve that you've endured during homework 1 and homework 2. You'll have annotated solutions to homework 2 later this week, and same for the quiz. Any questions, thoughts, concerns, riots? Anybody want to throw a tomato? No, not from class, and from Zoom you can't. Okay, so let's move on. So what we're doing here in Unit 4 is, first of all, oh, I got a tomato via Zoom. Well, back at you. All right, that's a nice emoji. All right, so in Unit 4, I spoke for an hour last week before you had Amy's marvelous lecture. I'll quickly recap what we did, and then we'll dig right into it. I think that within 2 hours, we should be able to cover quite a lot of ground. But of course, please stop me at any point if needed. The more questions, the better. Is it too loud for the folk in class? No? Okay. I feel like some very, very strong person like that. Okay. All right. Back to business. So what did we see? We saw the fact that functions in Julia have multiple methods. That's fine. We even got a feel for this type of generic function where this is not just a single function. This is like many functions depending what you put for t, as long as t is a number. I mean, you can't call this method with t being something that's a string, for example. It's not a number. We saw a few ad hoc things. We saw that there's returning nothing or just nothing in general as kind of a entity. It's good. Nothing, by the way, it's good to know. In other languages, does anybody know a name that you'd use for nothing? Put some other name in computer science, just to so we know. Say again. Void is one. Yeah, there's another. Null is 2, right? Null, void, depending, yeah, but right, good. Okay, this argument destructing is just a little syntactic feature, not important. Var args functions are important, so functions that don't have a unique signature, okay? Optional arguments we also spoke about, so then you can actually name the arguments, okay? This is, for example, very, very common in R, okay? So in the R language, you almost always use optional arguments. Keyword arguments, keyword arguments are very, very common in R, right? So arguments after the semicolon. So especially for functions like plot and something like that, you've got a variety of keyword arguments. The do block syntax, we also saw that. So here you've got filter and an anonymous function. So that first argument is an anonymous function. If that anonymous function is going to take a few lines, and instead of writing it in an ugly way like this, you'd sometimes see syntax like this. Okay, so this do means it's a function that has x as an argument. The function could have had multiple arguments, and it's given as the first parameter to filter. It's just, people would say syntactic sugar. The same with function composition and mapping, and the broadcast operator, which you've already used a lot before. And this is a macro, the @ macro. You've seen multiple macros before, and maybe towards the end of the course, you'll create a macro or two, especially with Andy. Okay, so macros are like functions, but they're actually not executed at compile time, but rather, executed at runtime. They're actually, their whole execution is done at compile time, and then they allow you to do other things that normal functions do not. So that's macros. So we won't cover macros today. And we stop pretty much here and more on control flow and just speaking about error handling. And there are about two and a half type things that we want to discuss here. So the first thing, I actually went to that last time, is this macro assert. So assertions are in general, when you're developing a program, a piece of software, something that runs, you have a model in your head of what's happening in there. There are all kinds of invariants that hold between the variables. You know, you're adding two things, so the result must be their sum, but there are, of course, other things, right? You're doing integer division, so you'll get a quotient and a remainder. So the dividend times the quotient plus the remainder needs to be the divisor, assuming I didn't flip dividend or divisor. Okay, so these are all kinds of rules that need to hold. You can make sure that they hold and then catch your bugs via asserts. Okay, so you'll see a few asserts in the project. So when you go to the project file, you go and look at the asserts, and we also use them in the unit testing. Must say, digressing a second to the project, in terms of software development methodology, okay, you've had homework 1 and homework 2. Well, homework 1 was Jupyter, and homework 2 was a few files, but it was still kind of not one piece of coherent software, right? It was multiple bits, okay? And you get to the project, this is the first time you're doing something that has a few files that speak together, but we're still not packaging them in one package. Okay, it's one GitHub repo, you can run them together, etc., but it's not one package. So the unit tests there are still not in the most kind of professional way. We're building up to that. In the next project, Andy will show you more, and then you'll actually see unit tests in a professional way. Okay, in a more professional way than what they are in the current project. But we're building up to that. So you'll see asserts there. So for example, here we're asserting that a matrix times its inverse is approximately equal to the identity. Why in the assert have it approximately equal and not equal? Yeah, it's floating points, right? So sometimes exactly. So if you're doing numerical computations, your assertions have to be of that nature, that things are only approximately correct. And this approx function, I think you've seen it before, it has multiple. You could have also called approx and then could have specified the error. I believe the error here by default is square root of machine epsilon or something like that. But let's go back to this function from the start. And this is a function which I call my 2x2 inverse. Not the most useful function in the world, but why not? So as an argument, it gets some A, and that A needs to be of a type matrix of float 64s. Okay, that's what it gets. So first of all, we have this line here. So what this line does is that's kind of, this is not assertion. This is checking that the input argument to your function agrees with what you wanted the function to do. So the size of A has to be 2x2. So how does this OR work? You've seen this more with AND. You've seen this short circuit evaluation with AND, right? But here, for this to happen, when will this be evaluated? Only if this is false, right? Only if this is false. We could have, how could we have written this via an AND? So what would I have changed here? Let me highlight this, and what would we have done here in terms of an AND? Just do a bit of De Morganish stuff. Yeah. Say again? Right. So if size of A is not equal to 2x2, and do the rest. Okay. Good. Thanks. All right. So now this is an error function, and the error function basically throws an error. Okay. So that's what the error. Not good, buddy. And we just threw an error. Okay, that's how you throw an error. Okay, so that's one thing, right? So instead of the function having some, the worst thing you want in software is undefined behavior, something that feels like it's running, but it's actually doing the wrong thing. When you actually get compile time errors, that's pretty good, because syntax errors are the best, because you know, after a while, after you know how to chase the brackets and things like that, you fix it. You actually want to have, you wouldn't want somebody to call this function on a 2x2 matrix and have it return on a 3x3 matrix and have it keep going. You'd prefer it to throw an error. Okay, so in general, functions should have error checking. Right up to a level. Okay, this is where the beef is. So what is this line? This is a determinant, right? So we're computing manually the determinant of a 2x2 matrix. Okay, and here we come to our second kind of sanity checking. Not all the 2x2 matrices have an inverse, right? For the matrix to have an inverse, you need the matrix to be non-singular. So if the determinant is approximately equal to 0, then we report the error. But here, we don't use the error function because, you know, it was legal to give this function a 2x2 matrix. It just happens to have linearly dependent columns or row, has rank 1. Okay, so what we do is we use the throw keyword. And what throw is literally like that. You're just throwing and you're saying, okay, this thing's not going to work. Leave, stop execution. And to whoever called me, throw to them this type of object. And this object is an argument error. Okay, and you can even put a little string in the argument error. The matrix is singular or near singular. Okay, so if I go here, I'll go to the help of exception handling. You've got all these exceptions that are being thrown, and you might have seen some of them. So you might have had your program, quote, crash in one way or another, and you've had some error like that thrown, okay? So, of course, an argument error makes sense because, well, it's, you know, the argument to the matrix A is not the best. Okay, and finally, if we pass this phase, then what we're going to do is we're going to do this. Flip the diagonal and put negative on the anti-diagonal and divide by the scalar determinant, and that would be the return value, right? So if we call the function on a ran 3x3, where was the error thrown? From which line here? See, it's from this line, right? If we now just do this, this is an assertion. Oh, that's fine. Oh, okay, sorry. If we give this this 2x2 matrix, which is just, I could have just done this 2x2 matrix is just 1s 2, 2, okay? So then we've got the argument error was thrown. So we get a bit more information, right? But the program still crashed, halted, finished, okay? In this case, the program, well, it doesn't finish because what, you might have seen the source code of how we do this. We use a package called weave.jl that just runs the thing sequentially and it, you know, it displays the output and it goes and it computes the next thing. You can see this if you go to the GitHub of the course. Okay. Now, here is the first time we're going to do something with this error and not crash. I mean, imagine that the spaceship flying to the moon, every time it needs to invert a matrix and the matrix is singular, abort mission. I mean, you'd have many movies of Apollo 13, right? So you want the software to catch these things and still survive. All right. So the mechanism for doing that is the try-catch paradigm. So in general, so this is a keyword. Yeah, this purple thing is a keyword. Okay, so this is another aspect of control flow that you might have never seen in any other language, certainly not in Julia. Okay, has anybody seen try-catch in other languages? Yeah, Java, Python, it exists in C++, etc. So in pretty much in all modern languages, you'll have it. Yeah, so thanks. So thanks for the comment in the chat. In Python, it's try except. Okay, but this form of exception handling, it's kind of become a standard paradigm. Okay, now what you do here. Okay, so what we're doing here, this is not the best example for try catch, but let's first of all look at it. So this is just so you see a bit something fancy. This is looping in nothing in 1 to 10. I iterate 10 times. I don't know why I did this. Just so you see an in, so we feel like we're good mathematicians. Here we're creating a matrix, a 2x2 matrix with the entries either the integer 1, 2, 3, 4, or 5. you don't need to try too much to create too many of these and have a matrix that's singular. Okay, because I mean, it's, you know, if you get, by the way, if you generate a uniformly random 2x2 matrix, it's never going to be really singular. Okay, up to 2 floating point numbers that are kind of falling within this, right? So the space of singular random matrices is 0. Of course, they occur a lot of in practice because matrices are structured, but this one has integers in it. And then this float function, the float function, that's a lowercase float function, broadcasted onto these elements just converts it to a float because that makes A a float. Okay, so that's just a way of creating these matrices. And then each time we're trying to invert. If this works nice, then we go to the next iteration. But from time to time, invert will do this throw. And out of these 10 times, it happened to do it twice. When it does this throw, this catch block catches E. I could have called this EX. I could have called it exception. I could have called it anything. That's the variable, which is the exception object, which was thrown. And the exception object is then, in this case, printed. But we could have done other things. We could have fixed ourselves. We could have redirected course. We could have told the user that's not good, etc. Okay. So you see here we crashed, finished here. When we did it on this singular matrix, here we gracefully continued. Okay. However, this is not really how you would use try catch. Okay, you often will not catch in the immediate context where you often will not catch in the immediate context where you try to do something. You'll more rather, this is kind of a bit more of a typical case, of course, also contrived, but let's look at this. So here again, we have a matrix of 1, 1, 1, 1. Clearly the determinant is 0, it's singular, you can't find its inverse. Okay, you've got a function of a matrix which does 10 times its inverse. Okay, that's F. You've got a function G of a matrix that applies F to the matrix, adds to it the constant 3. Why this dot? Because you cannot do matrix plus 3, you need to do matrix. This is not MATLAB, matrix dot plus equals 3, right? Element-wise broadcasting the addition of 3 to the matrix. You've got this third function which does twice times G of that matrix. So H is a composition, okay? Now, it might be that you're the one who did H, that's H is in your code, but F is actually, that has come from some package, from somebody else's code. So, you know, you've never seen F, right? You've already used quite a lot of code in Julia that doesn't come with base, and you probably didn't have time to go and look at that code. And that's the beauty of software development, right? You use other people's stuff, and if it's packaged nicely, you've done that. You did it with stats base, with distributions, with ODEs, with plots, with a bunch of things. Okay, so now when we're calling H of A, we get the exception. Of course, we could have now done a try and a catch here, okay, which we will in a second. So first of all, let's look at the exception. So you've already seen this many, many times when you were battling homework 1 and suffering through homework 2. Hopefully you didn't see it during the quiz. Okay, no, I'm joking. That was a joke. No jokes? Class for me used to be a whole bunch of jokes, but now the face masks, no students, and sense of humor has declined. Okay, that's all right. So, all right, so H of A here, we got the argument error, matrix is singular or near singular. That's our text. We wrote that, right? We wrote that here, matrix is singular or near singular. Okay, now what we get here is a trace of the call stack. What is a call stack? When a function calls a function, calls a function, calls a function, calls a function, the call stack collects these functions, and then when a function returns it, you go down the call stack and you put up more and you go down, etc. So that's who called who. So my 2x2 inv was called from the function f. Okay, and it actually tells us f is in this function f REPL 33.1. Because this is done in Weave, in the special typesetting software, you can't relate to it exactly where it is. Okay, but try it later in Jupyter or in the REPL or in Visual Studio Code, and you'll see exactly where the function f is defined. And then f was called by g, and g called f. Okay, and h called g, and finally the main was the top level scope that called that. Okay, so you get a winding all down the call stack. Now, alternatively, if we would have done this in a defensive manner, try h of a. So we tried H of A, same thing. At this point here, you'll have the exception thrown. The magical mechanism of exception handling is that it unwinds the call stack for you. Okay, so that's why it's not just like, okay, you know, if don't do this, it's not just an if. It actually returns from all those functions. And now we're back in the main function, which in this case is just main, and we continue. Understand? So when you throw, you're actually undoing all the things. Now, we don't have this in the examples. You might think to yourself, what if I have a function that opens a file, and that file is supposed to have JSON, okay? But the JSON has a syntax error. You know JSON now, experts in JSON, okay? The JSON has a syntax error. So I want to throw an exception JSON corrupt, okay? I want to throw an exception JSON corrupt. But when you open files, what's good practice also to do? You might have not done this, but it's if you have a program that's running for a long time, if you ask the operating system to open a file for reading, you want to, say again? You want to close it off, right? Thanks. I mean, why? Multiple reasons. Because your program, let's say you have a program that runs, you know, in the background for a whole year and it's reading input JSON files, right? And from time to time, it has an exception, and you know, it throws an exception. So it might not get to the code that closes it off, right? Because you did a throw. You said, I'm leaving, I'm going back. So if you really want to, look also at the exception handling code and look at the finally clause. The finally clause is for such cases to actually clean up nicely. I'm failing, but I just want to leave nicely. Okay? Yeah. Okay, that was a big rant on exception handling. Any questions, thoughts, anything from home? Anything from the YouTube viewers? You can't. It's done, it's finished. No? No questions? Okay, so the next thing we speak about is one of the most boring things, but also kind of important, and you're probably aware of it anyway, but let's just visit it a bit more, variable scope. Now, in contrast to the other things, if you go to the docs for variable scope, in this lecture, we're not going to be able to cover everything that's here. So there's quite a lot here. And frankly, this is written, the documentation for variable scope is written kind of more in a language specification manner than a user manual manner. So you don't really have to read it all. Okay, I'm just saying. So a lot of the things in Julia docs are very friendly. Variable scope is written more like a language specification. So just a few things to be aware of. I mean, when I studied programming for the first time, it was C a while, like, I don't know, 25 years ago. And, you know, there was local variables and global variables, okay? And in Julia, you kind of have the same thing. You've got variables that live within a function. They're local variables, okay? Things outside that function don't know those variables. And you've got global variables. However, you've got a few more nuances, okay? And we'll see now a few of these nuances, okay? So there's another thing, first of all, called modules, which you'll see with Andy in Unit 6. So that's just allowing to scope global variables and separate them. Okay, so you don't want to pollute. If you have a program that uses many packages, you don't want to pollute the namespace with dozens and dozens and dozens of variables. In general, you already got the hint for that. Global variables are a negative thing to use. Okay. But there are also issues in Julia, which, I mean, are designed, well, that's how the designers made the language optimal, so they believe, but I also believe. There are issues with the scope of variables where the scope also lives within for loops and while loops and within, yeah, pretty much that, within structs as well. We'll get to structs soon. Okay, so let's see this example. So here we have data. That's a global array, 1, 2, 3, because we're running here in global scope. But in general, this type of scripting of running in global scope is something that you're going to do less and less of, certainly in the 3 projects now. You're always going to run within a function almost. Okay, but we're running here in global scope. You've got a global variable data. And a lot of the things you've seen up to now were in global scope. Okay, so it's an array of integers. You've got S, it's an integer. You've got beta and gamma, that's 2 and 1, and fine. Okay, now we're doing a loop. Good. It's a loop that happens to be in global scope. Now, in this loop, our purpose is to sum data we'll get a weighted sum of data with respect to beta. So it turns out that if I, let's get this code and actually not go to Jupyter, we'll go to the REPL. So here I'm running this code, okay? So it turns out that if I would not have the global keyword, so let's see if I, oh, it's hard to do. If I'll run it again without the global keyword, so let me just, let's see if I can do this. And then, yeah, okay. So if I run it without the global keyword, I think I've already defined S as global. So, so if I run it without the global keyword, then this S, which we're changing, because it's inside a for loop, it will not be this S outside. Okay. So the global keyword here just tells the for loop this is S that's outside. However, in Jupyter, this is kind of a subtlety just to be aware of. In Jupyter, you're actually not running in global scope. So when I run this, even though it feels to me like I'm in global scope, Jupyter, which is supported with by iJulia, is already wrapping this thing I'm doing inside a function. Okay, so there's what I want to say is, okay, let's actually see this difference. Okay, so here I've run this, and in the end, S is 12. Okay, fine, that's in Jupyter, and I'm going to remove the global keyword, and S is still 12. Let's, because it's hard for me to do it in the REPL, let's open Visual Studio Code. Okay, and do file, new file, file save as, and we'll save it in your just so it goes on to the GitHub under the scrap notes. Oh, what did I call it? Global example.jl. Save. I think we're in business. Okay. So now if I do Shift Enter, is this not a Julia file? Hard for me to see here. Oh, it's saved as untitled. Sorry. File save as. It's just that the zoom is covering my window. Okay, I think we're in business now. No, don't do that. Do this. And where is it? Here it is. Let's run it. Shift Enter. Okay, so Julia's taking a second to run it. It's going to show us that S is 12. Okay. Whereas if I run it by with commenting this out, and just to be sure, I'll exit the session and run again. Okay. So let's see what happens. S is again 12. That's not what I wanted to see. I wanted to see an S is 0. Did I do this correctly? Or maybe I didn't save the file. Now I saved it and run it again. I don't know why. So S should have been, so now I'm surprising myself, S should have been here not a global variable. It actually should have complained that S is that it's trying to change S. I don't know. Okay, so I'll get back to you maybe via Piazza or something like that of what happened here that's surprising me. Yeah. Say again, say a bit louder. Oh no, but I'm running with the Shift Enter, so it's the same. But I could do that if you want. Sure. So press this. Oh, okay. So now, okay. I don't know. Good on what you said, but I don't know what happened before. But yeah, now it's complaining. So S is now global. Okay, so only thing I want to say is that we use a global keyword to mark S as global. Thank you. I don't know what happened previously. Well, now I'm debugging it, but that's okay. And that's how we color this as global. But there's more to it. Let's get back here and let's look at what's happening here. So here we've got the function some data with beta. Okay. Now you'll see this often that you give the argument name of a function. You've seen it before already, but it's now just repeating. You give the argument name of a function something that also exists outside its scope. In this case, there's a constant beta. It's 2 outside here. Okay, but when we do some data of beta divided by 2, okay, the function gets beta divided by 2, right? That's the internal version of beta. It's the local beta. It's not the global beta. Okay. Other things that you might see is that for here data, even though data is global, you actually do not need to use a global keyword, and that may be confusing. And the reason for that is that the elements of data are actually mutable, while the variable S is immutable. So here I'm trying to change a global variable, and here which is immutable, meaning you can't change it. We'll soon see mutable and immutable. And here I'm actually changing the elements of data which themselves are mutable. So you can change arrays. And that's pretty much what you have here. And of course, when you do here, one more thing to see here, S is defined as a local variable S, okay? But if you would have added the prefix global to it, then you would have had other behavior. It would have been the global that you have from before. So bottom line is, you generally want to think about scope. Often the language will just tell you, hey, this doesn't work, etc. But sometimes you can have all kinds of trouble where something global is contaminating something local in a function. And that's why in general, you don't want to work with global variables. So why do I say that? So you cannot change the S outside of this for loop, but you can see it, you can use it. So you might have clashes. Now, Julia also uses something called lexical scoping. You can get a link to that from the global docs, etc. And let's see something which I hope is an example for it. I'm not sure it's the best example, but let's see. So here we've got a function, my function. And here we're defining a function inside the function. You've seen this already before in these lecture notes. Anybody remember where we saw a function defined inside the function? Some example last week. It's above in the notes. That was in the polynomial generator function. Not polynomial like your project, but polynomial in the sense of just generating a polynomial based on coefficients, okay? So the scope of this function is this function, but here it's actually, you're returning it. You're returning it. And this function here does something with the variable x, which is a local variable to the function outside. So functions inside functions inherent scope, okay? And also for loops inside functions inherent scope. It'd be very difficult if you have a function and you have a for loop and things inside the for loop don't inherit variables from outside, okay? So when you have nested for loops, everything that's inside sees what's outside up to the function boundary. Okay, so now look, we set a global x, which is 20. And you might have thought, okay, what Julia does is it now compiles this thing, and it's going to do all kinds of things with x. In this case, it's just showing x, and it's going to look for an x someplace in the namespace, and we'll say, ah, x is 20. Yeah, what was your question? Yes, 100%. So that's what we're doing here. Yeah. So this is a function factory. Okay. So it's actually, even in your homework, you have this in the project. Sorry, you have this. You have a function factory. You actually need to refactor the function factory. No pun intended. Okay, so you need to get rid of that function factory. But yes, what you have here is a function. So let's go to actually, this is horrible with these examples that don't go anywhere. But here we had an example. This was like a real one. So we had the polynomial generator. Okay, the polynomial generator is like its name. It's a generator. It creates a function. It creates a polynomial function. It got an array of things. Okay, it's got coefficients. Okay, and it created this function poly, and it returned this poly, and then you can use that function. Okay, so functions are first-class objects. They can be moved around just like variables. Okay, so that's why in Julia, when you go when I go sum, right? And you know, I'm not doing sum of 1, 2, 3. Of course, this is sum of 1, 2, 3. But what if I do sum? So sum is now just that cell had the expression, the function sum. Okay, and that's function sum is an expression. It actually has 14 methods. Okay, so back to our. So thanks for the question. So back to here, we have. This function factory creates this function. Now you called my function, which gave you my function inside the function. It's called fret. Okay, so we renamed it. Okay, of course I can do other things that will be the name of the same thing. Okay. Oh, just so if you want to see that, then let's call it our sum equals sum. Okay, and our sum of 1, 2, 3. Here we've just created an alias. Okay, I'm digress for a second, right? So the our sum equals sum. So the variable handle our sum just points to the function sum, and you can use it just like sum. Okay, so the same thing here. You've got fret, and then I can execute fret. But fret said x equals 10, which was from the scope where the function was defined, and not x equals 20, which is the global scope. That's really a subtle issue, which frankly I wasn't aware of until preparing these lecture notes. So that's not the most important thing. We're soon getting to important things. Okay, so one more thing you might see is it's just a real subtle thing. So if you've got a loop, here's a while loop I going 1, 2, 3. Okay, and you do some stuff. If I now return I, what is I going to be? You've got like. If you've never seen the language, you can think it's one of two things. It's either 0, what it was before I entered the loop, or it can be 3, which is its final value. Most people would expect it to be its final value. That's what I would, because maybe you care, right? You did iterations and you wonder when was the last iteration, so it's final value. But no, you see that what it gives you is 0. So the reason is this I here inside the for loop is different to this I, which is external to its for loop. Okay, so these are all kinds of things that you might kind of break your head on one midnight when you're working on project 1, 2, or 3. Okay, so the scope of the inner variable I is going to live only for that for loop. I mean, if we wouldn't have the outer variable I, so let's actually do the same thing without the outer variable I. So let's do this. And just do this and see what happens. We even get, hey, I is not defined, right? Because I just lives within lines 2, 3, and 4 in this case. Okay. So Julia has this other keyword which you can use, and that's outer. Okay. And then that says that the variable that you're looping on in the for loop is going to also be the outer I, which exists. And then when you do that, you get a 3. Yeah, capiche? Anybody home? Questions? Got it? All right. Good. We're done with the boring stuff. You ready for the exciting stuff? It's very hard to tell excitement through face masks. Can you do something with the eyebrows? Nothing. Okay. All right. All right, let's do it. So types. So any language that respects itself and anything that's beyond basic will need to have types or classes or objects. You might have heard Amy here next week. You heard Amy here, not next week, last week, speaking about scripting versus object-oriented programming, etc. This course is actually not just about scripting. The scripting part is kind of finished, and now you're getting into programs with objects, with classes, with types, okay? And as you know, Julia has types. Okay, so, and soon we're within about 30 minutes, we're going to create our own types as well. So we'll deal with the system-defined types and create our own types, okay? which are synonymous with what you'd call classes in Python or Java or Swift or C++ or other languages that are object-oriented. Julia is not object-oriented per se, but it has types and it behaves slightly different. But you still get that same type of paradigm. All right, so let's start with some basic things. So type of 2.3, that's obviously float 64. You've seen that, and this is just a way to tell the literal 2.3 that you only want 32 bits for it. Okay, that's not so interesting. The type of 2 is an int64. And int64 is on 64, this is one subtlety with Julia, and once on 64-bit machines, which are most of our computers, it's an alias with int, okay? Whereas if you have a very old computer, then it will be an int will be in 32 bits. Okay, you might have not seen this yet. This is a rational type. Okay, so just when you do this double division or slash, it's a rational type. Okay, so 2/3, that's an exact representation of the 2/3. The whole unit that you're starting with Paul tomorrow, Paul Verbeek, right, deals with computer algebra and these types of representations of things like that. Exactly 2/3 is very important because you certainly don't want to do 2 divided by 3, which is 0.66666. By the way, around 200 years ago, the French wanted us to do base 12, and then we would have had 2/3 without continuing numbers. So, you know, but the world then settled on the decimal system, 10 fingers. Okay, so that's irrational. Now notice that when we do the type of this thing, it doesn't just say rational, it says rational curly braces in 64. In general, in Julia, curly braces deals with types, okay? And this means that it's the rational type parameterized within 64. I could have done int 8 of 2 divided like, well, not divided, rational int 8 of 3. And this thing is a rational of int 8s, okay? And I believe I could have also done 3.2 rational 2.5. No, okay, so rational only works on integral types, okay? So you can't do rational and put floating point types. Okay, so Julia says, I don't know how to deal with rational or floating point types. You might ask yourself, how does Julia differentiate between integral types and floating point types? Well, we'll see this soon in the type hierarchy. Okay, so here you have a complex number, okay? Again, this is a complex number of integer, real and imaginary parts, okay? And here you've got a complex number, which is actually complex F64, which is a complex of float 64s. Right? And this is, of course, a string, good. And this is a vector of ints, you've got that before. And this is a vector of float 64s, because once we put in the literals one non-integer bit, then it just decides it's float 64s. And this is what you call this is like a Python list. It's like a vector of any. Okay, so you've got a 1.0 and a 2 and the string 3. So this is a vector of any, like anything. Okay, so any is a type which is the mother of all other types, and we'll see that soon. Okay, so any type is any. There is an is a relationship. We'll deal with that. But in general, when you're dealing with vectors, you don't want to just have vectors of any, because then it's not as efficient and it's too heterogeneous to deal with them. Sometimes this is useful. Okay, you've got like a vector of ad hoc arbitrary things, but in general, if you have a vector of ints, it's much quicker to do computation of a vector of ints or a vector of floats. For example, if you're in Python, then what NumPy gives to Python on top of basic Python is moving from this vector of any called the list in Python. So if you don't care about Python, ignore this bit, okay, to arrays. Okay, that's a NumPy array is like a vector of ints. And you've also got this thing. So this is not the numbers 1, 2, 3. This is something called a unit range. And you've got a matrix. And even the names of types are valid Julia expressions, right? I can do float 64. And that is just the expression float 64. And the type of this thing is a data type. Okay, so the type name has itself a type. Okay, good. And we also know symbols. Okay, so we can work with symbols. Anything is a symbol. Okay, so anything that, sorry, that does, you know, hi people. Okay, this is a symbol. Right? So symbols are sometimes used to give options to things or to map things, etc. I think this is all things you kind of knew before already when you kind of got into when in the previous units, but now let's look at the structure of types. Now, a type can be abstract or not, and it can be concrete or not. And warning, abstract is not the opposite of concrete. Okay, we'll look at this. So types can be abstract and it can be concrete. I'll explain. An abstract type is something like real. Look, real is a real number, okay? But it's abstract in the sense that there's no computer implementation of a real number. A float 64 is a real, an int is a real, a bool is a real, a complex is not a real, right? So the real is just some abstraction of, oh, okay, that is, you know, all these things are real. But it's pretty good to have this abstraction in the computer, because if you make an algorithm that works on reals, why specialize to float 64s or ints? You just care about reals. What's the one difference, by the way, the big difference, like a difference? What do reals do that complex numbers don't do? Yeah. Order, right? You cannot sort an array of complex numbers. There's no is less than complex for complex numbers, but reals have an order. Okay, please don't. Anybody doing a course with Masood now? Math 2401. No, okay. Don't get into axioms of choice and all kinds of things like this. I don't, too complicated. All right. So that's an abstract type, okay? Now, a concrete type is a type that's defined and it's very well defined, and the complex, for example, is not a concrete type. So if I do is concrete type of, doesn't work, is concrete type of complex, I'll get a false. Okay. And the reason is, I can have all kinds of complexes. I can have a complex of an int. I can have a complex of a float 64. I can even have a complex of a bool. Okay, so the reason that the complex is a parametric type and hence it's not concrete, but it's also not abstract. Okay, it actually has an implementation. You'll see this. So first of all, this was just kind of a prelude to the fact that types can be abstract or concrete. Now, very importantly, we have a type hierarchy. So let's see this. Here is a number 2.3. X is 2.3. What's the type of X? We're taking a break, by the way, in a second. I know some of you are tired. Okay. What's its type? It's a float 64. Fine. We can ask, float 64, does it have any supertypes, any types that are parents of float 64? Now, in Julia, you don't have multiple inheritance. Okay, you don't have that a type can be multiple things. Okay, so you only have one supertype, but you can have several subtypes unless you're concrete, because then you're a leaf on the tree. So the supertype of float 64 happens to be an abstract float, something we call an abstract float. So an abstract float is an abstract floating point number. You can guess that it's not going to be a concrete type, which kind of, well, it's anything that has an exponent and a mantissa and exponent, mantissa, and a sign bit. Okay, that's like an abstract float, but it's not a concrete implementation of a 64-bit or a 32-bit or a 16-bit float. An abstract float, its supertype is going to be the real. And the real, guess what, is a number. What do you think the supertype of complex is? It's also a number, right? A number can be a complex or a real. Okay. And a number, its supertype is the mother of all types, any. Okay, in Java, the mother of all types is just called the object. Okay, it's kind of everything is the mother of all types. So that's like anything. Okay. So what's a supertype of any? It's also any. That's kind of the top of the tree. So what we did here is we went from a leaf in the tree, the leaf being float 64, and we went up the type hierarchy and we saw who are the parents of float 64s. And after the break, I'll put this here, we're going to look at this, at the program that does this and describes a type hierarchy. Okay, and we'll speak a bit more about that, and then we'll define our own types as well. Is there any questions before we take a break? No. Okay, enjoy the break. people at home didn't hear this. Okay. Sorry, the people at home didn't hear. I just answered a question about the write-up. The write-up assignment for the prospective seminars, you don't need to overthink it too much. It's a 1 to 3 paragraph write-up, which shows that you've followed the lecture, and make it coherent. It needs to be clean and with a point, but it's not the world's most challenging creative writing exercise. All right, any more questions before we continue? You can hear me at home? Homies. Yes, thank you. All right, so we were with types and we're starting to move around, and we understand there's something like a type hierarchy. Now, let me move just down here so we see the type hierarchy coming down from number. Okay, so just so you see this type hierarchy. You can also, if you go to, I mean, this is in many places, but of course I'll go to mine because I'm a bit biased. If you go to here, let's see, we have some figure of this. This is a statistics with Julia book. It has the PDF is still online. It won't be shortly, but if anybody needs it, just let me know. But anyway, this is a type hierarchy, right? So a number, a type hierarchy within numbers. Julia has way more than numbers, okay? Many, many things are types, but in terms of numbers, you've got complex and real can be abstract floats or integers or rationals or abstract irrationals. And most importantly here, an integer can be a bool. A Boolean is an integer, okay? 0 or 1, it's a very limited integer, but still much better than just a 0, okay? Can be unsigned and can be signed. And these guys at the bottom, they're concrete types. This complex is not concrete because you will see soon, because it can be parameterized by several other things. But instead of looking at this figure, look at this same representation of the figure, ignore those 3 things at the bottom. I'll explain what that is in a second. So up to here. You'll see in a few minutes the code that generates this thing. You've got number at the top. It's not concrete and it's abstract. And as children of it, you've got complex, which is not concrete, but it's not abstract. So you can actually create complexes, but they're complex. They're still not concrete because you've got a complex of a float or a complex of an int, etc. You've got real, it's an abstract, non-concrete. And under real, you've got abstract floats and abstract irrationals and integers. So all these reals have an order, right? And within, say, if you then finally get to like the unsigned, which is unsigned is short for unsigned integer, these are unsigned integers. These are all concrete types. They have a real specification. Now here at the bottom, we also have some other package, statsbase. Okay, you've used statsbase, I think, before. It has a few sampling functions, etc. And it turns out that statsbase makes a type which is called a p-value. This p-value you love from stat 1301 or whatever. Okay, and that's a type which is a concrete type which comes from, it's a subtype of, I think, real. Okay, and it also has a test statistic which is also a type. So when you create your own packages, because we have here in the namespace statsbase, you can also augment the built-in type hierarchy with other things. I mean, statsbase is kind of a standard Julia package, but it's still a user package. You can create your own statsbase. Okay, back up here again, there is an is-a function. So the is-a relationship in object-oriented programming is very important. So when you have something, is this, can you see this? Let's see. Is this an apple? Yes. So anything that you know how to do with an apple, you can do with it. Is it a fruit? Yes, there is an is-a relationship. Is it a living being? I don't know, unless you're a very extreme version of a vegan, then it's probably not. It's not a living being. Or maybe yes, let's not get in there, okay? So that's an is-a relationship. It's important to have an is-a relationship because if you now look at this window here, okay? So, or just think of graphical user interfaces. So graphical user interfaces will have things that will say, okay, this thing Is it a UI component? Is it a user interface component? Yes. Is this component clickable? Well, this one that I'm clicking, I guess I gotta click it here. Is it clickable? Yes, it's clickable. Is this component, is it a clickable component here? No, I cannot click it. Okay, so you've got all these relationships of things within a computer program. You'll see more of that. So is 2.3 a string? No. You can also use the is a function just like plus in infix notation. I think this is called infix notation. Okay, 2.3 is a float. Okay, so float 64, is it an abstract type? No, it's not an abstract type. Is it a concrete type? Yes, it is. Real, is it an abstract type? Yes, it's an abstract type. Is it a concrete type? No, it's not concrete. If you would have looked at these two code things, you would have thought, like I did actually naively a while back, that abstract is the opposite of concrete. But then you get to complex. Is it an abstract type? No, it's not complex. Is it concrete? It's also not concrete. The fourth thing doesn't exist. You don't have something that will be true and true. You won't have something that's both abstract and concrete. Okay, so you've got three options. Okay, three kind of general things. So if I do help on complex, I see that complex is parameterized. It's not concrete because there's not a specific concrete. It's parameterized by this T, and this T is anything that is a subtype of real. Okay. By the way, for is a, I can also ask int is a real? True. Int is a complex? False. Okay, etc. String is an any? True. Everything is an any. Okay, so that's also, this is a function. I should have had that in the notes. Okay, let's get to this nice little function here, that the nice application of recursion that's actually going to query the types. Okay, so there's also the function subtypes, which you just have built in, but in this environment in what is it called? Weave, the environment we create this notes with, you need to include it from interactive utils. This syntax, I don't know if you've seen, this just says use the package interactive utils. It's an inbuilt package, but not everything's in the namespace by default. And from it, use the function or the entity subtypes. The things that can be here would be typically a function, but it can also be a type or a global variable. So if I do subtypes, I think in this Jupyter environment, it just exists. Am I not too loud? Just double check with you. Okay. All right. So subtypes of real, here are the subtypes of real. Okay. So we've just seen abstract float, abstract rational, integer rational. These are subtypes of real. Let's look. Real, 1, 2, 3, 4. The 4 subtypes of real. Okay. So what we can do here is we can actually do a recursive function that would go through this type tree and do as follows. So we'll give it's going to show the type and its children. Okay, so we give it a type. We didn't annotate this, but this type should be like a data type. Okay, so the argument is actually a type. You know, you give it a type. It's a passable object, and we also keep its depth. So the reason we want the depth, we want to know how far in we are in the recursive call in the tree, just so we can print these things like this for the depth. Okay. By default, we start at 0. Depth starts at 0. And we say, if it's not concrete, then let's print not concrete. What does this thing do? It just prints dash, 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 dash to the power of depth. You can do strings to the power of something, string concatenation. Okay, print not concrete. And if it's an abstract, then say it's abstract, and then run on all the subtypes, because abstract types will have subtypes. Well, maybe they won't, but then it's kind of silly. Okay, they would typically have subtypes. So there's no reason to have an abstract type unless you subtype it. Okay, so loop on all the subtypes and make a recursive call on the subtypes. It's kind of nice recursion. And else, if it's here, you are not concrete. So you are. Sorry, you're not concrete, so you are concrete. So then say you're non-abstract. Is this correct the way I did? Oh, yeah, sorry, if you're here is abstract type. If you're non-abstract, then let's just make sure, this is assertion, this is to tell ourselves that the program's behaving like we want, that any type that's non-abstract will never have subtypes. You can only subtype abstract types. Okay, so that's a point here. You can only subtype abstract types. Else, meaning we are concrete, then also let's make sure there are no subtypes because concrete types are final. Julia is different here from Python, from C++, from Java, where you would have a class that would have some variables, some methods, etc., and then you inherit from it and you have a subtype and you keep the methods of the parent. Okay, so you could have said that this apple is a fruit. A fruit had seeds, so it had some variable num seeds. Okay, and I open this fruit, inside there's num seeds. In Julia, you have to implement every concrete type in the end. Okay, you'll see that a bit more. But what I'm saying is that only those leaves at the bottom are ones that actually have data in them. Okay, the rest are only kind of placeholders. Still, those placeholders are useful. Okay, and if it's concrete, you'll say it's concrete. So yeah, investigate this more. And it's also, if this course is the first time you've seen recursion, then investigate this more twice, because it's kind of nice how this just does a recursive printout through types. Okay, and I can do it, by the way. So look, let's take this code here and do this. And now let's do using distributions. I love the distributions package because I just love distributions. Okay, and let's do the super type of normal random variable. So that's a univariate. And let's do the super type of a distribution. I think maybe is sampleable. But let's call this function type in children. So this function has never seen the distributions package, but let's call it on the distribution. The distributions package defines a distribution type, right? I mean, you did this course on distributions. Maybe you didn't do stat 2003 and you didn't know all the distributions, but you did stat 1301, binomial, geometric, it's a collection of distributions. Let's look at so here is the tree of the distributions. Okay, it's quite a flat tree. Most of them are leaves, but you've got here all the distributions supplied as subtypes of the distribution. Okay, with a bit sometimes kind of second order children. All right, stop me if there are questions or anything of that sort. So a type can be mutable or immutable. It's important for the language to have things that are immutable, meaning they don't change. So variables that are immutable are important for reasons of consistency and performance. So you'll probably hear more about this from Andy as well when you get to Unit 6. But in terms of where things are stored in memory, when you run a Julia program, it can be stored in two general places. One is on the call stack. Remember, we saw the call stack of functions, but each function has its own local variables that are stored in the call stack. So sometimes things live in the call stack. And the call stack's actually quick. So it's quick to put things on the stack. It's quick to take them off. Everything there's memory locality in the call stack, and that's quick. But the other place where things are stored is called the heap. As Paul Bellet said a few weeks ago, not to be confused with the data structure heap. There is a heap also called the free store. So when Julia allocates memory for you, it takes a heap. So this is all places inside this little computer, okay? But the RAM is partitioned. The operating system knows how to do call stack and heap. So immutable things that cannot change, live on the call stack. Mutable data lives typically on the heap. That's kind of a general distinction. So you can just query, and you don't query a type in this case, you query a variable which has a type, okay? So x equals 7, you know that x is an int. Is it immutable? Yes, it's immutable, okay? So, sorry, is it mutable? Is it mutable? Is x mutable? It's false, okay? So 7 is a constant. That means that now if you take another variable and you say that also equals x, both of them point to the same place. Okay. But the array that has 7 in it is mutable. Okay. Now let's see how this plays a role. So let's create here 2 versions of the function f. When I say 2 versions, I say 2 methods. Hello, Kaylee Nazarati. Okay, so let's create 2 methods. All right. So this method gets an integer. This method gets an array of integers. All right. The reason we used here begin and end, but this is just a function. Okay, it's just you could have just written this in multiple lines. All right. So here what we do is we get z, and we set z to 0. Here we get an array z, and we set the first entry of the array to 0. Very different, right? Let's look at this. X equals 1. Type of x is in 64, is immutable. That's going to be true. Okay. Before we call the f, which we'll call this method, okay, we get a 1 on x. Then we say, hey, set x, which, well, it's x here, but it's z is there. That's fine. That's the argument we pass to the function. Let's set it to be 0. After we call it, the x outside, which happens to be the global x, is still 1. So this is sometimes you might call in other languages, that's called by value. You actually pass an argument, but the argument is copied. Now, the nice thing about Julia, and that's the same in Python, it's not copied, it's immutable, so it can just give it a pointer to the place on the call stack. Like if, you know, x here is just 8 bytes, okay, not a big deal to copy it. But if x was a struct with, you know, 5k, it doesn't have to copy it because it's immutable. It cannot change. However, let's look at the array x, a very degenerate array, nevertheless, an array. All right. The type of x is an array. A vector is an alias of a one-dimensional array. Okay. Is an array of int64s. Is it mutable? Is it immutable? I hate this question. Is it immutable? It's false. No, it's mutable. Okay. You pass now x to f. The second method of f will be called this one. What this method does, it simply gets an array. Of course, if the array was length 0, you'll get an exception here because we're trying to change something. Okay, this is the first index. You all know by now that Julia starts indexing by 1. Okay, you change the value of the array. After the call, you've actually changed the data. Okay. You might have been aware of this type of thing before, you might have not, but it's a major thing. Okay, you pass an array to a function, it's actually going to change the value of that array. Now, of course, this is there's reasons to do that because sometimes, you know, you won't want to pass maybe an image to a function and you want to take all the points in the image that are too intense and you want to zero them out or do something. You want to change the original image. You don't want to make copies. Okay, keep in mind that that's a type of behavior. You just want to see a similar type of thing to that. Look, I've got my array here is 1, 2, 3. And I've got your array, well, it's just the array. I'll go your array in the second position equals 100. And let's look at array. Okay. So both array and your array, and this type of behavior also exists in Python and many other languages, etc., pointed to the same memory in the heap that had the values 1, 2, and 3. Okay, and so even if I changed your array to, that's just a reference to this thing. I set it to 100. If I look now at the array, it's set as 100. So the same thing happens with the passing of arrays to a function. Yeah, you don't seem surprised. That's 6:20 in the evening, nothing will surprise you. All right, so of course, sometimes you want to pass an array and you'll see that in your project, or you want to pass some data, but you don't want to dirty it, okay? So make a copy, make a copy. How do you copy an array? Yeah, you can make your own function that will copy, but there's also the built-in function copy. So here's, let's go through this example very, very quickly. it'll have copy, and it'll also have the other function, deep copy. Okay, so these are two built-in functions that exist with many, many methods. And of course, you have copy and deep copy for arrays, but you have them for other things as well. So you have a variable A10, B equals A. Both B and A point to the same things, but B and A are immutable. So once I changed B, I'm actually creating a new thing. I cannot change this 10. Okay, so if I show A, you didn't have any kind of overriding behavior. However, if A is an array, that's the same type of thing we just saw, and B equals A, and you change an element of B and you show A, oops, you actually changed B. Sorry, that change of B changed A. If you don't want that to happen, either like this in global scope or within a function, then use copy. Okay, so A is 10, B is a copy of A. All right. Now, if I change the first element of B and I show A, I didn't touch A. However, look at this thing. Now, what is a type of A now? What's a type of A now? What's a type of A? Roughly. It's a vector of a vector of A. Perfect. Right. That's a type of A. Right. Yeah. Perfect. Vector of a vector of an int, which is an alias for a one-dimensional array of a one-dimensional array of an int. Perfect. All right. So now when I copy A into B, what I'm doing here is I'm entering the first vector. Well, it only has one, but I'm entering the first vector and the first argument, and I'm changing it to 20. And I'm changing A. Oh my God, I still changed A. So the reason is copy only copied the first level of values. And so it copied the pointer to, or the reference to this other vector, but it didn't create a distinct copy of this thing. That's what we copy by default is a shallow copy. You can use deep copy, which will do recursive copy of the object up until it gets to immutable things, okay? And then this type of behavior won't exist. Okay, so just be aware of deep copy. So if you have a complicated data structure that has a lot of things inside it, you want to create a complete different copy, you want to use deep copy. Okay, so why did we touch all this? Well, we spoke about types and we said types can be mutable and immutable. And then there's these subtleties if you make copies of them or deep copies of them, etc. Now, finally, I promised something interesting. Let's get interesting. Let's define our own types. They're not going to be very interesting types, but they'll be example types. Okay. So the way you define your own type in Julia is the struct keyword. Okay, or if it's an abstract type, you use the abstract type keyword. We'll see that in a few minutes. Okay. So this is a new type I've defined, and that type is a person. Person is much more than height, weight, and a name, but that's the person we have here. Okay, so a person is a type which is now a composite type. It has multiple things. It has a height, it has a weight, and it has a name. Float 64, and a string. When I construct a type like that, Julia immediately gives me a function, and the function name is the same name as the type. And that function is called the constructor. Okay. Now, other object-oriented languages, or other languages that are object-oriented, I should say, have within a type like this might be the class keyword sometimes, and you also have methods inside the types. Julia, no, there's no methods. A type is just data, except for the constructor method. So the constructor method is a function with the same name of the type, and the convention is for names of types to typically use capital letters. Types and packages and modules should be capital letters in contrast to variables and functions, okay? And the constructor, the default constructor just had this was a height, this was a weight, and this was a name. And the variable is person. What's the type of person? Well, it's capital person. Then you can access the fields using this dot. The dot is not the broadcast operator. The dot is the subnaming or field accessing operator. Okay, so person.height, person.weight, person name. Okay, that's how you create your own types. Looks simple, it is. Structs are by default not immutable. So is mutable will give us false, right? So if I try to do person.weight, if the person gained weight, in this case, went from 78.6 to 85.4, and I do this assignment, I get an error. The error is set field. Person is something I cannot change. Julia gives us another keyword called mutable. We didn't need to put here immutable. That is default. Structs are by default immutable. But if you want your struct to be mutable so you can change the field names, say mutable struct. Okay. And I called it a different name here. It's mutable person, not person. Not the best name to call it mutable person, but that's okay. So again, I have the constructor, and now I can override the weight. I can also print the person if I like. Okay. So that's creating our own types. Now, notice that during the same runtime, and Julia, that's quite annoying, I must say, you typically cannot redefine your type. So you'll find that as you're actually programming it in the homework and projects, no more homeworks projects, you're going to change the thing of the types, and you run Julia again without exiting the session. Julia say, and if you change from mutable to immutable, or if you added a field name, or you change the type of the field name, Julia will get mad. Okay, so you can't do that. There is a package called revise.jl, which you can use to allow you to do that in VS Code. Maybe Andy will speak about that in a few weeks. But for now, just start and stop your session. Okay. Now, here is, what are we showing here? So here's another types, my struct. Okay, struct, by the way, stands for structure, and back in 1970s in the C language, before there was C++, there were structs. Okay. And then what C++ did, it took structs and it made them classes. So they also had their functions. They also had their methods. Okay, but Julia is kind of moving back to the old days. There's only structs. However, there's multiple dispatch, which gives you a lot more. We'll see that soon. Okay, so this is here. Oh, here we're seeing the error. Here is my struct, and if we try my struct again, you get invalid definition. Okay. All right. Questions? Anything? Thoughts? Excitements in the air? Yeah, I see eyebrows. Thank you. That's all I need. Okay, so now let's make a bit of a type hierarchy. Not the most useful in the world type hierarchy, but you'll extrapolate to that, especially in project 2. That's coming up in a few weeks. You'll create a type hierarchy. So let's now create also our own abstract type. This was a concrete type. Yeah, so if I do, let's just run this here and do is concrete mutable person true. Okay. But you can also create abstract types, and you just use a different syntax for this. You say abstract type. You don't say abstract struct. You say abstract type, name of the type, and it's a bit funny. That's the way it is. So this just tells Julia there's something called animal. Okay, can't do anything with it just yet, but we soon will. And we can create a type hierarchy. We'll say, well, okay, animals. Well, there's a mammal, which is an animal, and it's still abstract. Okay. Abstract type, a mammal is an animal. A reptile is an animal. A human is a mammal. This one is concrete. It has fields. You can really create data. You can create data of that human. Okay. The human has mammal. It has a height, a weight, and now we changed. We don't have a field for the name string. We just to diversify. We have religious, true or false. Actually, you know, it can be, I don't think religion is so binary, but let's say it's true or false. Okay. A dog, we didn't give dog the field religious, although they might have their own religion, I don't know. Okay, so struct dog is a mammal. All right, height and weight. Whenever you get to the concrete types, this is actually people that come from other languages would say, hey, that's a bit funny. Why didn't you just have height and weight inside animal? Because any animal has height and weight, unless you're like a tapeworm, you just have length, okay? But even tapeworms have height and weight, all right? So in Julia, you actually have to do this repeating, and in software development, we hate repeating things. When you find yourself copying and copying, copying, repeating things, software development is all about reuse and generalization. You don't want to repeat things too much, but here, look, both human had to define these fields and dog had to define these fields. That's the way the language is. There are pros and cons with it. The pros you'll see, I hope the pros soon, you'll get a feel from soon. But people from other languages, so for example, in Python or Java, C++, Swift, etc., you would have had those fields, height and weight, up there in animal, okay? The dimensions of an animal. Of course, you can actually create height and weight. You can create another struct on the side, which you'll call dimensions, and you'll just put the struct dimensions to be part of human or dog, right? So you can put types inside types. The fields of inside a type don't have to be primitive fields. They can also be fields that are user-defined types. Let's now create another type, which we'll call the flex dog. So this is what you call a parametric type. This parametric type is not just one type. It's not a concrete type, and it won't be an abstract type. This is the one that's not concrete and not abstract. It's parameterized by t, and t is anything which is real valued. And it is a subtype of mammal. So it's just like a dog, but maybe instead of keeping the height and weight in float 64s, you'd prefer to use int 16s. So you'll have a flex dog of int 16s. And let's also create a crocodile, which is a subtype of reptile, okay, as you'd expect. So it has, in this case, it's not height and weight. And then you see, okay, at least this argumentation I said against having kind of everything in a concrete type, right? A crocodile, instead of calling height and weight, maybe you have length and weight. And the type here, don't confuse the word type with this word type that I've been saying like a zillion times. This type is just the type of crocodile, and it's a symbol, okay? And it can be maybe saltwater or freshwater. Now, it's nice that after we did this, we can use our function we did before, and it actually prints for us a whole type hierarchy, which we just created, okay? So we've just created a type hierarchy of things. Questions so far? Thoughts? All right. So when you create crocodile, there's no constructor, okay. Why is this? So when you create every type, you get, by default, you get a gift, which is a constructor. So if I do methods of crocodile, I think this is wrong. So if I'll run this, I'll only see one method. I won't see, oh no, okay. I get two methods for crocodile, just one, it's the same method with length, weight, and the type, or length once in the type that are generic. But these are both, you only get this one constructor. So I can create the crocodile TikTok. Does anybody know the crocodile TikTok? Apparently I looked, that's a crocodile from Peter Pan, you know, the bad crocodile. Well, I think, no, Captain Hook was bad. TikTok was just an accessory. Okay, so this is a crocodile here. So we created this crocodile on salt water. But we can also create our own constructor. So this thing is called, thanks, Alexander. So this thing is called an outer constructor. So constructors can appear inside the type specification or out. So when you have a function with the name of the type, and you now don't have the default one that kind of has all the arguments of all the field names of the type, because by the way, your type can have like 12 field names. So what you'll want a constructor which gets like 12 things as arguments, you know, it's hard to construct this way. So this is just a crocodile that only gets, again, the word type is confusing here, it only gets a symbol, which you expect to be either saltwater or freshwater. And it says, if the type is saltwater, then it will use the other constructor and will kind of use the default values. Okay, and maybe this is an average saltwater. I didn't go to Wikipedia for these values. If the type is freshwater, I'll create another crocodile. Oh, I made a mistake here. This should be freshwater. Okay, what I'm highlighting here should be freshwater. That's a mistake, sorry. Okay. Else, then you'll throw an error. You know how to throw an error. So now crocodile, methods of crocodile, there is the two ones that came built in, and there's also just crocodile on a symbol. So we know how to construct a crocodile. In the same way, moving away from this exciting fauna, if you've got the normal distribution, that was one constructor, and you've got the normal distribution with a mean of 2.3 and a variance of 1 point, or a standard deviation of 1.5. That's a different constructor. Same thing. So or same analogy. Okay, crocodile, saltwater. I need to fix this. So saltwater should be freshwater, etc. You can do crocodile of ice water. Okay. Okay, now constructors in general, there's all these nuances and subtleties in constructors, and read them as you need, and maybe you'll do a bit more with Andy, but there's all these variants and nuances of dealing with constructors, like constructor functions. So there's documentations for constructors here. What I'm saying is now, we're not going to be exhaustive in our description. Now, we also had the parametric type, FlexDog. Now, this is a nice thing. FlexDog, remember FlexDog is kind of cool, FlexDog. FlexDog has T, which is real, and you can have different types of FlexDogs. You can have FlexDogs with integers, with floats, etc. Anything that's real. Okay. So if I do here FlexDog of 2, 4, Julia already knew that I'm giving it integers. So the type of this thing, dash, that's the name of our dog, by the way. Not so yeah, he is flexible. Not so. Okay, so anyway, that's an int64 dog. Okay, but if we take last year dog and you put float 32s there, then it creates a FlexDog of float 32s. So what Julia does with this parametric type is in runtime, it instantiates different versions of that type for the specific thing that you want. And it's actually very versatile in this way, because you can, well, just many things of packages work with all kinds of type T's that you've never, like we could have done FlexDog. Of course, FlexDog is not a very algorithmic thing. It's not doing too many things, but maybe there's a different type of number that's not the ones that exist, right? Maybe it's some other abstraction of a number, integers mod P. Okay, you could create a FlexDog with that, and the code will still work. So that's the thing about this parametric type. All right. Now, if we try to create, for example, an array of FlexDogs of complex values, you'll say not work because complex is not a type of real, right? So FlexDog was flexible, but only so flexible. It didn't accept these arguments T that are not real valued. And complex is false. It's not true. All right. Let's get to polymorphism. So this is like object-oriented programming, but it's not really object-oriented in the sense that it's not packaged as object-oriented, that you have your structs are not classes, that they have functions. Okay, so in an object-oriented language, and it might be that that's a language you've worked with before or will in the future, then you might add methods to the types, which will be make a noise. Okay, make a noise, right? Like in this GUI that you're seeing here, okay? In this GUI, there is, or let's open my Finder. This is a GUI, right? Each one of these menu elements is a type GUI element, and it has all kinds of methods, how to display, what to do when it's clicked, et cetera, et cetera. In Julia, you would do this externally to the type. You'd make a function animal noise, for example. But the animal noise can still be dispatched using multiple dispatch based on its type. So animal noise of dog will print woof, and human says hello, and crocodile, I don't know what noise it is. So it's like, shh. Anybody know? I don't know. Something. I don't know. Something like that. Okay, so that's a crocodile. Okay, so in these menu elements that you've seen, of course, you're going way beyond these animals, right? Each one has their own appearance, etc., and they might be of different types because this thing, or this GUI element, which is this whole kind of sub window, is not the type of this thing, which is a button. And it's not the type of this thing, which is maybe a different type of button, or a type of this thing, which is a pull down menu. But they still all have that same method. To implement this, the paradigm is called polymorphism. And it's basically keep a collection of things that are more abstract than your concrete thing. In this case, we're keeping a collection of animals. Okay. And the animals in this case, I'm just instantiating, it's an array of a crocodile, saltwater crocodile, a human, a crocodile, and a dog. It's like Noah's Ark here. Okay, that's what you got, this animals array. Right? The type of this array is an array of the common denominator of all these things, which are all animals. Okay, they're not even mammals, right? Now I can map the function animal noise, in this case, broadcast it to each of animals. And look, I'm getting, for the first one, I'm going to get the, for the second one, I'm going to get hello. For the third one, I'm going to get again, and for the fourth one, I'm going to get woof. Okay, so this type of thing, this kind of thing in object-oriented programming is called polymorphism, and you see it implemented in Julia in this following way. Okay, so that is one reason to kind of have this abstract type. So you know that every animal makes a noise. Okay, almost every animal. Okay, maybe for one of them there's like return nothing, right? But you treat that array as an array of animals. You don't know what the specific animal noise function is. Now I can have this in my package, which is package animals, and then somebody else will come and add to that package and make more animals with more animal noises. And I've never seen, they just need to have the function animal noise, and they need to add more methods to the function animal noise. Okay, so the methods of animal noise, there's animal noise so far for 3 things. Yeah. Okay. You can also do notice that we left FlexDog outside. So you can create a union type. A union type is like a type which is either dog or FlexDog. Okay, so this function, animal noise, works for either dogs or FlexDogs. Okay, it works for either or. That's a union. You could have had multiple things in the union type, and they're also going to be woof. And let's add this FlexDog, a new FlexDog UN16 to animals, and do noise, and it's going to do woof. Okay. Of course, you could have had these functions deal. I mean, this does woof, right? But of course, you could have had this woof function do a big woof or a small woof, depending on the dimension of the dog, right? So you could have dealt with the specific fields, right? Back to this GUI. The fields of this thing, this drop-down menu, are different than the fields of this button. Yeah. All right. Okay. Questions? Can you hear me at home? It'd be funny if not. Not funny, sad. We haven't had a Zoom loss yet. You can hear. Thank you. Okay. All right. Just a bit more. All right, so now we get to methods in multiple dispatch, which you've already seen multiple times. Okay, so of course you know that you've got a myf on an int, and you've got a myint on a float, and you can apply it twice. Okay, so I don't know actually why this is here. So it's just here so you could look now in methods in the Julia doc. So at this point, I mean, this is kind of an overview of a few things in the Julia doc. So at this point, I suggest you go to methods in Julia docs and have a bit of a look at how this is readable. So that's not a very big read, and have a bit of a read. And you can have parametric methods. We've already seen this, and we'll see it more. So just like you have parametric types, you have parametric methods. Okay, we'll see more of that. Okay, so now that we kind of understood types a bit, let's now go to existing functions, such as a function plus or other functions, and augment the types we create with methods of the existing functions. Okay, that's what we're going to do now. And you'll see a whole bunch of this in your project as well. So we'll finish in 16 minutes, 15 minutes, and 7 p.m. Brazil time. Okay. So, as you probably know already, almost everything in Julia is kind of implemented in Julia because Julia can compile it down to LLVM, which is then compiled to very efficient code. Julia could then actually make low order things like addition actually a call to a function. So when we do 2 plus 3, it actually called the function plus of xt. And now you understand this a bit more, where t is one of these integers, you see? So that was the method. There was a specific method plus. You can go to it in line 87 in int.jl in the Julia source. And it works on plus of things, of types, of adding two things that are of this kind of the integral type. If you would have done which plus of floating points, it would have done a different methods. If I do methods of plus, it gives me a list of methods. There's at the moment in the system, let's just redirect this into the function length or length of methods plus, or 271 pluses. So let's create another plus, okay? If you do this in C++, that's called operator overloading. It just means that you can use nice syntax of arithmetic. If you do it in Python, I think it's called magic methods, yeah? All right, so we want to now do plus with our own types. This is not a great example, but here it is. So here is a type which is player score. It has a player name and it has a score which is an integer. So I'm a player and Johnny is my name, 22 is my score. Okay, here is player score Johnny. If I do me plus equals 10, I wanted to increase the score by 10. Okay, it actually tried to do plus of player score on int64. There is no function of all these 271 methods. There's not a method of doing plus and int64s. So let's create one. So let's take the inbuilt function plus and add to it another method. When we do this to things that exist in other packages that we use, in this case, it's a package base, we need to use the import keyword. So it's not like using base. When you run Julia, you have using base by default. Like all the things that are in package base are already default. Import is like using, but you can also create different methods. And there's a few more subtleties for the differences between import and using. But that's in terms of the way they use it, that's good enough. So if I want to create another method for plus, I'll do import base plus. Of course, this plus didn't have to be like some funny thing like the symbol plus. It could have been the name filter for the function filter. It could have been push exclamation mark. It could have been sort. It could have been any inbuilt function, okay? And now we're creating the function, the method definition for plus of a player score and an integer. Okay, and this returns a player score. Now, I wrote this here in 3 lines, but you could have just written this in 1 line. You could have just written plus equals this return value because it's 1 line. All it does is it creates a new player score. Which function does it call now? What's the name of this function, or what is it? What is this thing I'm highlighting? This is a function call. What did we call this function that creates a type? The constructor, thank you. It calls the constructor of player score, keeps the same name, okay, but increments the score with n. Now, you might have also wanted to create the opposite version, which creates an int in a player score, and you could have defined that, but I didn't do it, okay? So now when I do me plus equals 10, there's no function plus equals in Julia. Julia plus equals, the language takes plus equals and says me equals me plus 10, okay? And it increases the player score by 10. So we've just created plus for player score. You have the same type of thing in your project 1 for polynomials. You're adding polynomials, multiplying polynomials, doing all kinds of stuff with polynomials. Okay, let's now do a bit of pretty printing. So when we print stuff in Julia, Julia calls this function, calls this associated method of the function show. Okay, So when we print or when we do string manipulation, so when we get the string representation of a type, right? I mean, you guys already know, you know, like float is a bunch of bits, right? But you do string representation, it does something. It calls show on the float. The show function in Base, so you can, let's look at all the shows that exist. Methods show, whole bunch, probably 304. So, you know, we could show a whole bunch of things. Okay, a lot of these things we don't know exactly what they are, but all these things have their special show. Okay, so show gets as input something which is like an IO stream. It's this abstract thing that we don't really need to deal with. It's like the stream, which can be the standard output or the standard error or a file or a stream into a string. So this is just the type of thing that show gets. And now we're creating, and again, we're now augmenting show with our additional method, and we'll do show of player score. And what we're going to do is we're going to print into this stream. This stream, again, it might be when somebody calls show, it might be std out or it might be into a string. Okay, and the way, instead of doing playing score this, we want to do score for player name equals player score. So now when we have me here was a player that had name Johnny and score 32, we have some score, me pretty good. So you see this string here came from from the show method. Part of what you need to do in the project is to take, we have polynomials and they're printed, but they're not printed beautifully. You'll see why they're not printed beautifully. You want to, the first thing you want to improve the pretty printing. Just it's a small bit, yeah. Shouldn't take too long. Okay, so you'll do a different implementation of the show. Okay. Questions about this? All right, let's just see a bit more. Okay, so let's assume now where we want to collect data. Okay. And we also want to do running statistics. All right. So I'm going to go through this quickly just to finish it off and just so you get a few more examples, and that closes this unit. All right. So this is like a hypothetical thing. Let's say our data is just, you know, numbers uniformly distributed between 0 and 100, but that doesn't matter. And you've got some array of data, an array of float 64s. And this function collect and use data runs for 100 time units, but think of this 100 might be like a zillion time units, okay? And every time it gets a new data point and it pushes the data, and from time to time, in this case, like every 20 time units, you want to print the mean of the data. This is from the statistics package or the maximum of the data, okay? Okay, that nothing special here. So collect and use data. After 20 steps, the mean is already close to 50 and the maximum is already close to 100 as you would expect. And as you continue, you know, the mean would be around 50 and the maximum is a bit closer to 100. Okay. All right. Let's assume now that instead of doing, I mean, the inefficient thing here, if this was like a million, if this was a billion, this 100 was a billion, and this was quite frequent, and every time this mean and this maximum is a bit of a hypothetical example, but not really, okay? This mean and this maximum has to look over all the data. So let's do what we call running statistics, online statistics, running statistics. So in addition to keeping the data, we'll also keep the mean and we'll update it dynamically, and we'll keep the maximum. We'll update it dynamically, okay? So let's create a type for this. So we'll call this type running stats data. Okay, so I just wanted to have this type here that's kind of slightly more connected to reality. It's not a crocodile. I mean, not that crocodiles are not in reality, but you know, not the most important thing. Okay, or an animal. Okay, all right. So this type has data, which is a vector of float 64s. That's fine. It has a mean, it has a maximum, and it has this thing. What is this function again? We said it before. The constructor. However, here you're seeing something you haven't seen before in the code above. When we do a constructor, and this is the nuances which come with constructors, when you have a constructor which is inside the type, it's called an inner constructor, inside the type definition, inside the struct. You want like a constructor which gets no argument. There was a default constructor which got like 3 things, data and mean and max, but you want a constructor which gets nothing. You then use the new keyword. this is a keyword, which is specifically for this type of thing, for inner constructors. That's it. We're almost done with the Julia keywords. We're going to see it. Okay. And this creates a running stats data with a empty data. And let's set nans and nans for the mean and the max. All right. And the new keyword means something else in other languages, like in languages like C++, it's to allocate memory. Okay. Here it's to create a new, but it's like to create, it's just Julia had to find a way to kind of call the default constructor on the running stats data. Okay. And there's a function show summary, which gets running stats data, which shows the mean and the max. Okay. So here, if we created like data, running stats data, of course, there's nothing in it. So the mean is nan and the max is nan. Okay. Now, what we can do is we can take the maximum function from base. We can take the push exclamation function from base. We can take the mean function from statistics, and we can create our own methods for these functions. Okay, here we created a method that works on running stats data, which is not, there's no other function, show summary in some other package. But here we're going to create our own methods of these functions. Okay, so maximum of running stats data is, of course, very easy. All it does is it just pulls the field max and returns it, right? Mean is also easy. Okay, push is where we have to work. Okay, so here when we called push on an array, you know, this push, what it did, it just added an element to the array. Of course, the inner implementation of the array is quite smart. It saw if the allocated memory is finished, then it allocated another place of memory and it did a whole bunch of copy. It typically allocated double as much or something like that. Okay, but our pushing into this thing needs to do some updating, some smart updating. So what kind of updating is it going to do? So you now are pushing into this thing with a new data point. So first of all, add the data point to your whole collection of data. Of course, you could have had a version of this thing that doesn't keep all the data, but this thing both keeps all the data and the running statistics, so they have very quick access. Okay. Now you say a few kind of edge cases. You say, if the data point is greater than what you had in the max, well, sorry, that's not an edge case, but if you have a new maximum, or this, why did I highlight this? Or what's this highlight? For the first time, right? For the first time, right? So, or it's empty, then the max is going to be the new data point, okay? Thank you. Let's update the mean. So let's get the length of the data. Of course, we could have kept this as a field, but it's kept efficiently in the vector anyway. Okay, so how many points are in there? And again, if it's the first point, if the first observation, then the mean is just going to be the first observation. If it's not the first observation, then let's do this formula, which, come on, of course you know it, right? You've seen it before. Running mean. If you take the sample mean, you take the sum and you break it from the sum of I1 to n, you break it I1 to n minus 1 and the last one, and that's how you compute the running mean. Okay, and then you compute the running mean. Now, the nice thing is that our experiment function, the one that kind of dealt with the data here, you know, before data was an array. And in an array, we knew how to do push exclamation mark, we knew how to do mean, we knew how to do maximum. Now, and in this function, we actually didn't specify the argument type. It was a generic function. Okay. Anything that has push exclamation mark and mean and maximum goes with this function, which is like our collect and use data, our life. Now we're going to do collect and use data. So collect and use data, and literally, I first wrote this, and only later when I wrote it, I wrote this. So I didn't go back and update collect and use data. Right? Collect and use data existed. I just ran down and then wrote this. Now we're going to do collect and use data on this data, which is running stats data. And it works just the same. You can compare the numbers. Let's look at that one, 50.79, 50.79. But of course, this new one is, well, more efficient and less efficient. It's less efficient if you insert a lot of data points and you only compute the mean and the max only once in a while. But it is very efficient if you insert a lot of data points and every 100 or 20 or 50 or so, you compute the mean and the max, and you've got 1 billion points in there. Okay. And we won't get to this example, but look at this one. This is still, when we wrote this thing, this still had, it was kind of hard coded. It's float 64s. And the data is float 64s, and the mean is float 64s. But what if my data is something else? What if my data is ints, or something much more complex, or things that have intervals, okay? So here is a version of it, flex running stats data, where t is any number. So it will have a vector of t. The mean still needs to be float 64. The mean of integer values can be float 64, but the maximum is going to be t. And this is just kind of ugly syntax. That's a parametric constructor. But this thing still works, and now only the data here is integers. Okay, so when you finish, the last thing you're not going to see here, and this, I recommend you look at this by yourself, and ask me in the consultation hour or any other time. So this is for data structures where you have structs that point to other structs of the same type. In this case, this is like a graph-based data structure. Okay, so you'll have nodes in a graph, and each node points to a vector of other nodes, which are its friends, and you can play around with that. And that's the end of the unit. Ran a bit late. Any questions? Sorry, I spoke a lot. No? Eyebrows, nothing? Okay, have a good one. You'll see Paul Verbeek tomorrow. I speak slow relative to him, I promise. Okay, bye-bye.